In this video, we're going to do a very quick introduction to acids and bases. So the first thing we want to talk about are acids and what makes an acid an acid. Generally, when we think about an acid, we think about generating H plus ions in solution. That's generally what we think of when we're dealing with an acid. You can often recognize acids in the formula because they often lead with an H. Now, what does that mean? That means if you're looking at the formula of a compound and doesn't automatically make it true, but it's true 98% plus of the time, if you got an H leading off in the formula and then the rest of the compound, you're probably going to be dealing with an acid. So that kind of gives you a key hint right away that you're going to be dealing with an acid. We know that acids can, depending upon their strength and type, be caustic and corrosive. One of the other physical properties we sometimes associate with acids is that sour taste. So some of your sour tasting foods, things like lemon juice and vinegar, have that sour taste to them because they're very acidic. Now you have foods that are very acidic that aren't quite as sour. If you compare orange juice to lemon juice, orange juice is still pretty acidic, but we don't consider it as sour generally as lemon juice. Well, that's because there's more sugar in the orange juice that masks and hides some of that sour taste. Acids are going to come in two different types, strong acids and weak acids, and we're going to look at each type. First up are the strong acids. We can kind of think about the strong acids the same way we did the strong electrolytes. The strong electrolytes completely break up into ions. Well, the strong acid is going to completely break up into ions, and one of those ions is going to be the H plus ion. There are only 6 common strong acids that you're ever going to run across. There's actually a handful more, but those are fairly rare. There's 6 common strong acids. So what that means is it's easiest to memorize those 6 strong acids, the names and the formulas, because there's billions upon billions of acids, but if there's only 6 strong ones and you know those, it's easier to identify those that are not going to be strong as well. So if it's not on this list, then you can assume it's not a strong acid, it'll be a weak acid. So your strong acids are going to be those on the list, and you're familiar with a lot of these. Hydrochloric acid is HCl, hydrobromic acid HBr, hydroiodic acid HI. You may be familiar with nitric acid HNO3, sulfuric acid H2SO4, perchloric acid HClO4. These strong acids are strong electrolytes. So if we take one of these strong acids, we'll pick HBr in this case, and we show what happens when we place it in water, well, it's going to break up into ions, H plus and Br minus ions. Well, those H plus ions are what make this an acid, and because it completely breaks up into ions, remember the arrow's only going in one direction, that's what's going to make it strong. So if you had 100 units of HBr, you would create 100 units of H plus ions. If you had 1,000 units of HBr, you would create 1,000 H plus ions. We can also have weak acids. Weak acids, easiest way to identify those is recognize that something's an acid and then see if it's on that list of those 6 strong acids. If it's not on that list of the 6 strong acids, then it's going to be a weak acid. So we want to memorize those strong acids because everything else will be weak. We don't want to memorize billions of different weak acids. It's much easier to memorize the 6 strong acids and then recognize those that are not strong must be weak. What makes these weak is the same thing that makes weak electrolytes weak. They'll partially break up into ions. I'm going to pick an example that you kind of have already seen. When we did weak electrolytes, we used HF as an example of a weak electrolyte. Well, HF is also a weak acid because one of the ions it breaks up into is these H plus ions. Now, how do we recognize that this is weak? Well, from the formula, we would say HF is not in that list of strong acids, therefore it must be weak right away. We also recognize that instead of the arrow going in one direction, we have the arrows going in both directions. We have the equilibrium arrows. Both things are happening. Remember what that double-headed arrow actually shows you. Your double-headed arrow shows you a partial breakup of ions. And remember, it's not a 50-50 breakup either. It's much more heavily favored towards this side without the ions. Such that if we started with 100 units of HF, we would only make 2 or 3 H plus ions out of that because most of it's going to stay on the HF side. Very little is going to go to the ion side. When we look at bases, we have a couple different ways we could actually define bases. One way of defining a base would be that they generate the OH minus ion. Remember, that's that hydroxide ion. But we can also think about bases another way. We can also think about bases as kind of being the opposite of acids. So if acids produce or generate H plus ions, then bases need to do the opposite. Bases are going to absorb H plus ions. Kind of think of them almost like sponges that can suck up H plus ions. Just like the acids, the bases also come in both strong and weak varieties. Your bases can be caustic and corrosive. Bases also tend to be a little bit slippery. So a lot of your cleansing agents, your soaps, your shampoos, your detergents, your body washes, your liquid hand soaps, your bar soaps, those slippery type feeling things are slippery because of the bases in them. And again, we shouldn't just be going around tasting random things, but bases also tend to be a little bit bitter. So when you think about something like super dark chocolate, one of those 100% cocoa without any real sugar added to it, it has a very bitter taste to it. That's from the bases that are in there. Let's go ahead and look at our strong bases. Our strong bases, we know what strong means. Strong means completely break up, or do it well, or do it a lot. They completely break up to directly produce hydroxide ions. Now, how can we identify the strong bases? Any sort of ionic hydroxide that you can look at. If you can take an ionic hydroxide and dissolve it into water, it's going to be a strong base. You can see the hydroxide ion directly in the formula. We're not going to memorize lists. We just have to recognize what are ionic hydroxides. So it's going to be hydroxide ion paired with some sort of positive ion. If that ionic hydroxide dissolves, it's a strong base. Some examples: sodium hydroxide, potassium hydroxide, barium hydroxide. Here we have hydroxide ions paired with positive ions. These are all soluble. These are all going to dissolve and be strong bases. You can see the hydroxide ion right in the formula. NaOH, you can see, strong electrolyte. You recognize that already as a strong electrolyte. Well, if it's a strong electrolyte and it's going to produce OH minus ions, not only is it a strong electrolyte, it's going to be a strong base as well. So how do these strong bases work? If we pick one of them, we'll pick potassium hydroxide as an example. It's a solid. When we dissolve that into water, it's going to split up into potassium ions. It's also going to split up into the hydroxide ions. And it's going to completely dissolve and completely break up into ions, such that if we had 100 units of potassium hydroxide, we would make 100 hydroxide units. That's that strong piece. They're going to produce a lot of OH minus ions because they're going to completely break up. Remember, this arrow's only pointed left to right one way, showing which way this is going to go. We can also have weak bases. Weak bases produce OH minus ions in a different way. We would say these weak bases produce these OH minus ions indirectly. And this indirect reaction is through a reaction with water. Because it's an indirect way, that makes these weak bases a little bit more difficult to identify. So these weak bases can be tough to identify. But I'm going to show you a way of identifying weak bases based upon some things we already know how to identify. So an example of a weak base is F minus ion. So F minus is a weak base. Now, right away, you may be looking at F minus and saying, where in the world does that hydroxide ion come from? I don't see it. And that's good, because you shouldn't be seeing it right now, because it's not directly in the formula. You're not going to see hydroxide ions in the formula in the same way you would the strong bases. Weak bases generate these hydroxide ions in an indirect way through a reaction with water. And here's that reaction. So F minus, remember we talked about one way bases kind of act as the opposite of acids. So bases can grab H plus ions. Well, if F minus reacts with water, if you remove an H plus ion from water, so if F minus comes in and grabs an H plus from water, what are we going to have? Well, F minus plus the H plus that it grabbed would make HF. After the F minus grabbed that H plus, what would be left behind that was originally the water? Well, water would have lost an H plus, so that means it would be left with OH minus. There's our hydroxide ion. The hydroxide ion gets produced from F minus removing an H plus from that water molecule. So F minus grabbed the H plus from the water molecule, and that's how that OH minus ion is going to be created. Notice we're dealing with weak. When we're dealing with weak, what are you seeing? You're seeing the double-headed reaction arrows, that equilibrium arrow. What's that showing you is that that doesn't go completely left to right. In fact, most of it stays on the left. If we started with 100 units of F minus ion, we would probably only get 2 or 3 units of hydroxide ion. That's that weakness. That's a weak base. That's a weak electrolyte. That's those double-headed arrows are showing you it's only going to do it to a very, very small extent. These weak bases can be very difficult to identify, but there is a technique that we're going to talk about to identify them. We can identify these by using what are called conjugates. So we want to talk a little bit about conjugates. So what conjugates are is conjugates are a pair of molecules who are related through the presence or the absence of an H plus ion. Now, a lot of times people make conjugates more complicated than they need to be. That's what they are. It's a pair of molecules, and their relationship is that one of them will have the H plus ion, one of them will not have the H plus ion. So let's look at some examples of some conjugate pairs. So HCl and Cl minus are conjugates of each other. Okay? The difference between HCl and Cl minus is just the presence or absence of the H plus ion. On HCl, the H plus ion is there, and Cl minus, it's gone. You do the same thing for HF and F minus. HF and F minus are conjugates of each other. The HF has the H plus ion, the F minus does not have the H plus ion. HNO2 and NO2 minus, again, are an example of a conjugate pair. The difference between the two is either the presence or the absence of that H plus ion. HNO2 has the H plus ion, NO2 minus does not have the H plus ion. So here's how we can use the idea of conjugates to identify weak bases using something we already know. Weak bases are conjugates of weak acids. We know how to identify weak acids. So being we know how to identify weak acids pretty easily, we're going to use that to identify weak bases. So how do we use that to recognize that F minus was a weak base? Well, what's the conjugate of F minus? Well, conjugate of F minus would just be stick an H plus on it, F minus, and what do you get? Well, if we stick an H plus on F minus, we're going to get HF. Well, what in the world is HF? We can very easily identify HF as a weak acid. It's not a strong acid, it leads with an H. So right away we know that F minus is a weak base. The conjugate of a weak acid is a weak base. That's just how we're able to identify these weak bases. We have to go through what is its conjugate and what is that conjugate. Now, you might be tempted then to kind of use some, kind of word games to say some things that wouldn't be true. So I said that weak bases are the conjugates of weak acids. So what would the conjugate of a strong acid be? Now you may be thinking, well, the conjugate of a weak acid is a weak base. Maybe the conjugate of a strong acid should be a strong base. Well, that would be incorrect. Or maybe you'd say, well, the conjugate of a strong acid should still be a weak base. Well, neither of those are correct. The conjugate of a strong acid is nothing. Not nothing in that it doesn't exist. It's nothing in that the conjugate of a strong acid would have no acid-base properties to it. So let's kind of look at this. If we have a strong acid, HBr, we showed how it's split up into H plus and Br minus. Well, HBr and Br minus are conjugates of each other, right? HBr and Br minus are conjugates of each other. They differ in the presence or absence of that H plus. The HBr has the H plus, the Br minus does not have the H plus. But the difference here is that HBr is a strong acid. That's going to make Br minus nothing, and here's why. What do we know about strong acids? Well, strong acids completely break up to produce the H plus ion and then the counter ion on the other side. So Br minus, as a result, cannot be any sort of base. Why can't it be a base? Well, what do bases do? Bases end up grabbing H plus. Does this bromide have any ability to grab this H plus? The answer is no. That bromide is incapable of re-grabbing that H plus. Why? Well, if it were capable of that, we'd have a reaction arrow going the other way, going from right to left, which means we wouldn't have started with a strong acid. So the conjugate of a strong acid does not have any acid-base properties whatsoever, but the conjugate of a weak acid will be a weak base. Kind of want to make sure you go through and you kind of think about that. The conjugate of a weak acid will be a weak base. Think about those equilibrium arrows. Both things could happen. But the conjugate of a strong acid has to be nothing because there is no equilibrium arrow. The reaction only goes one way.